Okay, good morning everyone. So in the previous class we were, am I audible? Is the screen visible?
Yes, sir.
Yes, sir.
Okay.
Yes,
So
sir.
in the previous class, we started with AC fundamentals, right? So we discussed about what is the difference between AC and DC, and what are the different types of AC, that is single phase and three phase, and what will happen if you consider or if you connect a DC supply to a transformer, and on that basis, we mentioned that AC is, you can say, slightly more advantageous than DC, given the fact that the voltage levels in AC can be easily manipulated, and the manipulation is not so easy in case of DC systems. Okay, but on the flip side, we had also seen that in the near future, DC may phase out AC. Okay, not the usage, the transmission I'm saying. Okay, the transmission of DC may phase out the AC transmission. Okay, all right. So today, let us discuss about the generation of AC. Okay, how the AC is generated. Okay, so let me write the subheading. Now, AC is generated, okay, using a device called generator. So AC is generated using a device called generator. AC generator. Okay. Now, what is this generator? So you can consider this generator as a black box. So let me write it as generator. As a black box, you don't worry what is present within this generator. Okay. In the second half, I will tell you what exactly you mean by a generator. Now, to this generator, some power is given as the input, and upon receiving the input power, it gives some output power. Now, to produce electricity, okay, that means to say this generator should give you AC waveform. That means to say the power output should be electrical energy. Okay, in short, it should be some voltage. Now, to get electrical energy as the power output, what you have to give as the input, because you have to convert the energy from one form to the other. You know that the output energy should be an electrical energy. So the input energy, as your friend mentioned, it should be something like mechanical energy. Okay, energy. In case of DC, okay, or if you consider a AA battery, okay, a simple pen cell battery, you produce electricity using the chemical energy, right? Due to the electrolytic reaction, what happens is that the ions are going to get circulated in the circuit. So in case of AA battery, the chemical energy is basically converted into electrical energy. On the other hand, in case of AC generation, the mechanical energy is converted into electrical energy. How? So in order to have mechanical energy, okay, what we have is a generator. Okay, now that's what I was talking about. A second level, there's too much noise. Let me close the door. Okay, now let us try to open up, okay, the generator. So I'll not consider generator as a black box. I will consider it something like white box. So this generator basically consisting of two major parts. two major parts. Stationary part called as stator, and a rotating part. Okay, this stationary part is kind of fixed. Okay, and a rotating part called as rotor. The inside part is called as rotor. Okay. Now, in case of generator, the working is something like this. Since rotor is free to move, okay, what they will do is that the rotor, okay, is connected to a turbine. Let's say this is your turbine. Okay, very basic diagram I will draw. So it is just for the sake of understanding I'm drawing. This is your turbine. On this turbine, let us say we are making a water to fall. This is say water. So in hydroelectric power plant, this is what happens. So water is made to fall on turbine blades. So what will happen when the water falls on the turbine blade? This turbine starts to rotate in one particular direction. Now attached to the turbine, what do we have? We have the rotor. When turbine starts rotating, the rotor starts rotating. Let me use a different color so that you will be able to distinguish. And let me zoom the figure. Yeah. When the turbine starts rotating, the rotor starts rotating. The rotor starts rotating. Okay. Now this rotor will have several electrical conductors. This rotor will have several electrical conductors, and these electrical conductors are under the influence of magnets. Some north and south pole I will represent. So north and south pole, they are magnets. So basically what is happening is that when the rotor under motion, right, this has conductors or coils, one and the same. Okay. Now the conductors are rotating in a stationary magnetic field, due to which what happens? Can anyone tell me? You have studied about it.
Electric flux, magnetic flux.
Yeah. So the north and south pole, they are magnets. So they produce magnetic field. So basically, when the conductors are under motion, the magnetic field is getting cut. And due to Faraday's law of electromagnetic induction, there will be an induced EMF. And that's how the electricity is produced in case of power plants. So in power plants, this is how basically the electricity is produced. So generator basically works on the principle of electromagnetic induction. Electromagnetic induction. Now, in order to produce EMF or electromotive force, there should be some motion in the conductor. So that's the reason the induced EMF is called as dynamically induced EMF. The induced EMF is called as dynamically induced EMF. So all rotating generators, they work on the principle of dynamically induced EMF, okay, which is on the basis of Faraday's law of electromagnetic induction. Okay, I think you have studied about dynamically induced EMF, if I'm not wrong. Is it correct? Or have you heard of dynamically induced EMF? Can anyone confirm?
Yes, sir, I have done so.
Okay.
I taken electronics in 12th, so it was there.
Okay. So this is how the EMF is produced. Okay, you are not expected to repeat this particular explanation in the exam. This I have told you for your understanding's sake. Okay, so that being said, now we can go to the next topic. Okay, that is how an AC waveform is produced. Okay, fine. So what we will do is let me construct a simple diagram. Okay, so there's no circle. Circle is my bottleneck. Okay, still okay, into shape. Okay, all right. And let us consider two pole pieces. Some north pole. Let us consider this as north pole and this as south pole. Okay, so this diagram I'm drawing. Okay, so to make you to understand how exactly the electricity is produced. Okay, so the orientation of flux lines is something like this. Okay. From north to south pole. I'll have to draw multiple flux lines. Okay. Okay, so north to south pole, the flux orientation. All right. Okay, so the magnetic field basically represents the stator part of the machine or stationary part of the machine. On the other hand, this circular object, okay, it represents the rotating part of the machine, which is called as rotor. Okay, now this rotor or the rotating part of the machine, carries several conductors. Okay, now let us consider the case of a single conductor. Okay, let us say that a single conductor is placed in position 1. Okay, in position 1. And when the rotor is under motion, okay, so when the rotor is under motion, what happens is that the conductor keeps on rotating. Okay, now the place at which the conductor occupies the position is pretty difficult to predict, right? Because it constantly rotates with some angular velocity v. So where v is the angular velocity, let us claim now only angular velocity. Okay, now let us assume certain positions for the conductor. Okay, let us say at time interval t equal to 0, the conductor occupies position 1. At some time interval t, okay, so at t is equal to 0, let us say the position is 1. At time t is equal to, say, I by 2, let's say the conductor occupies position 2. Okay, and let's say 3 pi by 2, sorry, at pi interval, let's say at pi interval it occupies position 3. and at, let's say, 3 pi by 3, sorry, 2 pi by 2, let's say it occupies position 4. Okay. So there can be multiple positions, but I am considering few definite positions. Okay, say 1, say this is 2, say this is 3, and say this is 4. And let us also consider, okay, some random position, okay, say somewhere here. Okay, so where this is at, some random position, omega t is equal to some theta 1, or simply say theta, which is measured from the reference axis. So this is the inclination angle theta. And let us say this is position 5. Okay. Now, we have assumed different positions. Okay. Let's say it is along x-axis, then it occupies y-axis, then again comes to x-axis, then again negative y-axis, and comes to the rest position, which is position 1. Then we have also assumed a position, which is inclined at an angle theta with respect to the reference. Okay. Now, over here, the aim is to find the induced DMF. What will be the induced DMF? Okay, by the generator when the conductor is placed in position 1. Okay, so that can be evaluated something like this. So what you have to do is you have to understand the tendency of motion of the conductor. Okay, let us assume that the conductor is rotating in anti-clockwise direction. Okay, so this is the direction of rotation. Okay, anti-clockwise direction I have assumed. Now, at position 1, when the conductor is there in position 1, the tendency of motion is something like this. The conductor tries to rotate, in this direction. That is straight upwards. Okay. From that position, it tries to move. So the tendency of motion can be considered as vertically upwards. Now, at this particular, movement, you can see that the conductor is trying to move parallel to the flux line, isn't it? So at position 1, okay, let me write it so that same thing can be converted into notes. At position 1, conductor tries to move parallel to the flux lines. Okay, now when the conductor tries to move parallel to the flux line, will there be any change of flux or will there be any cutting of flux? No cutting of flux. If there is no cutting of flux, then the change of flux, that is d phi by dt, is 0. And as per Faraday's law of electromagnetic induction, the induced EMF is proportional to d phi by dt. This is law 1, right? Law 1. So induced EMF in position 1 is 0 volts. So whenever the conductor tries to move parallel to the flux lines, the induced EMF will be 0. Okay. On the other hand, when the conductor occupies position 2, okay, the tendency of movement is basically, left bound. So in this position, that is in position 2, the conductor tends to move in what direction? Again, left bound only, because we have considered the anti-clockwise. But the movement, you can say that it is perpendicular to the flux lines. In position 2, at position 2, conductor tries to move perpendicular to the flux line. When the conductor moves perpendicular to the flux lines, what happens is that maximum flux gets cut. That is something like, the rate of change of flux is maximum. Okay, and therefore induced EMF will be maximum. So E can be taken as EM volts. All right. Are you following what I'm trying to tell you? Or did I lose you guys?
No, sir.
No, right. You're following, right?
Yes, sir.
Yes, sir.
Yeah, fine. Now, when the conductor, let's say, reaches position 3, okay, because the direction of motion is anti-clockwise, right? So at position 3, the conductor, tries to move vertically downwards. Now at position 3, the tendency of movement is basically, once again, parallel to the flux lines. So the conductor is trying to move parallel to the flux lines. Hence, there will be no cutting of flux and there will be no change in flux, due to which the induced EMF in position 3 going to be 0. So at position 3, you can say conductor is parallel to flux lines, therefore no cutting of flux lines. That implies rate of change of flux is 0, and therefore E, which is proportional to d phi by dt, is 0 volts. Okay, so that means to say, whenever the conductor occupies a position where the movement of the conductor is parallel to flux lines, the induced EMF is always 0. Okay. On the other hand, when the conductor occupies position 4, the movement of the conductor is in such a way that the conductor is trying to move, perpendicular to the flux lines, and therefore induced EMF going to be maximum. Okay, but now the EMF induction is going to take place in the opposite direction. Okay, because the orientation of the conductor is now downwards, right? So conductor moves perpendicular to flux lines, therefore maximum flux lines are going to get cut. Okay, that implies the rate of change of flux is maximum, and therefore E is equal to EM. Okay. Left to right, E is equal to minus EM volts. Okay. Negative sign indicates that the conductor has changed its direction. Okay, now the conductor has occupied the negative y-axis, right? So indicates that the conductor has changed its direction. Okay. And when the conductor reaches to its original position, okay, that is at position 1, EMF becomes 0, okay, so and so forth. Okay, so this keeps happening one cycle after the other, and due to which, several cycles of AC signal is going to get generated. All right, fine. So this is the basis in which sinusoidal EMF is produced. Okay. Now, what if we consider a position, okay, which is having some inclination angle theta with respect to the reference. Okay. So what I will do, I will just zoom this particular position, that is position 5. Okay, because there is no space to resolve the vectors. Okay, so I'll just consider at position 5. Okay. Say these are the flux lines. Okay. And let's say this is the reference. Say we'll keep the circle somewhere over here. And let me consider a single conductor in position 5. Okay. Say this is the origin. Okay, and this is angle theta. Let me zoom a bit. Okay. Now, the tendency of motion is, kind of tangential, right? Tangential it is. Tangential. So this is how the velocity component of the velocity tries to be in, right? Tangential. Now, what we can do is, this velocity component, we can resolve into two components, the x component and the y component. The x component going to be something like this. Okay, you have studied resolution of vector, right? And the y component going to be something like this. Okay, so let's say this is Vy, and let's say this is Vh. Okay, now this angle is theta. If this angle is theta, then what is this angle? Theta, because z angles, right? So this is also theta. On the other hand, what is the angle between the velocity plane and the inclination plane? Okay, so what I'm trying to tell you is that what is this angle? Can anyone tell me? It is tangential, so it is 90 degrees. Correct, no? It is tangential. You can follow this, right? This is tangential. So angle between V and this inclination is 90 degree. Therefore, this particular angle, the acute angle, is basically 90 minus theta. 90 minus theta. So once we have this angle, you can write an expression for the horizontal component as well as vertical component. So your horizontal component can be written as V cos 90 minus theta, V cos 90 minus theta, and your vertical component can be written as V sine 90 minus theta. Okay. Now, you have two components. The question over here is that, are these two components, okay, contributing in the EMF induction? If you look at the vertical component, okay, the vertical component, let me write Vy, is parallel to the flux lines, right? So this is parallel to the flux lines. And therefore, d phi by dt is 0, and due to which E is equal to 0 volts. So the vertical component doesn't take part in EMF induction. That's because the orientation is parallel to the flux lines. On the other hand, if you look at the horizontal component is perpendicular to the flux lines. Correct. And when the flux lines are perpendicular to when the orientation is perpendicular to the flux lines, there will be induction of EMF. Therefore, E is present. That is, induced EMF is present in the conductor. Okay. Now, this can be given on the basis of dynamically induced EMF. That is, dynamically induced EMF can be given as E is equal to BL V sine theta. So here the velocity component is B into L into, let me write VH, where VH is V cos 90 minus theta. So cos 90 minus theta is sine theta. So E is equal to BLV sine theta. So the induced EMF in some arbitrary position 5 is E is equal to BLV sine theta. So basically the movement of the conductor, okay, movement of the conductor in a circular path traces sinusoidal signal. In the sense, it follows sine law. Okay, so this is how the AC voltage is going to get developed whenever a circular rotor moves in a constant magnetic field, or vice versa. Okay, in the sense, you may have a stationary conductor system and you may have a rotating magnetic field. That is also possible. So to produce EMF using dynamically induced EMF principle, either your magnetic field should be rotating with stationary conductor, or your conductor system should be rotating with a stationary magnetic field. Okay, so either one of these are rotating in nature, then we will have a physical motion. And the moment when we have a physical motion, the resultant induced EMF, we are going to call it as a dynamically induced EMF. Okay, so this is the thing. Okay, so generation of AC waveform. Okay. Is it understood, or do you have any doubts?
Sir, I have one doubt.
Okay.
Sir, if we take other positions, will be EMF will be same?
No. Other position, the EMF will not be same, because in arbitrary position, what happens is that the EMF totally depends on the inclination angle. Okay, the greater the inclination angle, greater will be the EMF production. In a sense, when theta is equal to 90 degree, okay, it is
Maximum.
position 2. Correct? No.
Yes.
in position 2, the maximum EMF gets induced. So E becomes BLV sin 90. So E is equal to BLV, which is taken as EM. Okay. So lesser the inclination angle, lesser will be the induced EMF. Greater the inclination angle, greater will be the induced EMF.
Okay, sir. Thank you.
Okay. So now that we have come to know about the EMF value at different positions, what you can do is we can trace a sinusoidal signal. Okay, so we'll try to trace a sinusoidal signal. Okay, so to trace the sinusoidal signal, what we will do is first we will draw a circle. Let me use white color. Okay, this is called as rotating phasor concept. I will introduce phase concept sometime later. So let's say this is our x-axis, sorry, y-axis. And let's say this is our x-axis.
Excuse me, sir.
Yes.
Sir, when we say that an EMF is induced, where exactly is it induced?
In the conductor. In the conductor it is induced. Okay.
Okay, sir.
Let me draw one more axis somewhere here. Okay, and then just let me show you the projections. Say the projection of position 2 is somewhere over here. So in a previous discussion, I had considered different positions, right? Now these positions I'm writing once again. Just a minute, I'm receiving a call. Yeah. Right. So what was this position? Position 1, right? And this is position 2, and this is position 3, and this is position 4, and some arbitrary position 5 also we had considered. Okay. Now, this is something known as the concept of rotating vector. In the sense, your AC signal can be assumed as a vector which is constantly rotating in space. Okay, and the vector length basically represents the maximum value of the signal. Either it represents maximum value of the voltage or maximum value of the current. Okay, so what we will do is, let us consider the origin as, let's say, O. Okay, and let us place a vector, okay, with length O1 along x-axis. Okay, so something of this I'm doing. I'm placing a vector along x-axis. Okay, pretty difficult to overlap exactly along x-axis. So be it. Now, the length basically represents, okay, length of O1 is the maximum value of the signal. The vector length basically represents the maximum value of the signal. Say length O1 is equal to Vm volts, where Vm is the maximum value of the instantaneous voltage. Right? So this is our instantaneous voltage V, and this is our time axis. Okay. Now, in this concept of rotating vector, what we are supposed to do is that when the vector is rotating in space in anticlockwise direction, okay, with some angular velocity or angular frequency omega, we have to keep on collecting its projection, and we are supposed to place it on to this two-dimensional space. Okay, so when the vector is under motion in the anticlockwise direction, what we have to do is we have to collect its projection, and we will have to map it onto this two-dimensional space. In the sense, when the vector is along the direction, or along the direction 0, 1, the projection of the vector is basically the origin. Okay, this is called as the default position of the vector. On the other hand, when the vector is rotated in anticlockwise direction with an angular frequency omega, and when the vector occupies position 2, its projection in the two-dimensional plane going to be, can anyone tell me where I am supposed to do its projection in two-dimensional plane? Can I do the projection here or somewhere else?
From origin.
Yeah. So the default position was position 1. Now you have rotated by an angle of 90 degrees. So what you have to do is you have to measure this angular displacement basically. Okay, suppose this is 90 degree or pi by 2 radians, one and the same. Okay, and at this point you are supposed to show the projection. So this is the projection of the vector at position 2. Similarly, when the vector is rotated by further 90 degrees, what will happen? The vector is going to occupy position 3. Okay, so the total angular displacement from the initial position is 180 degree. Okay, so what is the projection at position 3?
0.
0. But where you are supposed to place that 0?
Pi.
At pi interval, pi radians, exactly, good. So this is pi or 180 degree, and this is the mapping of the vector. And when you further rotate the vector by an angle of 90 degree, the vector is projected along the negative y-axis, and the total rotation, okay, going to be 180 plus 90, that is 270 degree or 3 pi by 2 radians, right? Or 270 degree. So the corresponding projection you're going to have somewhere over here. And when a further 90 degree rotation is given, okay, the vector, I'll use a different color now just to distinguish, not the blue, let's say the orange. The vector will come back to its original position. Now at this position, what is the projection? your y coordinate going to be 0, but your x coordinate going to be 360 degree. So 360 degree is somewhere here. So at 360 degree or at 2 pi radians, or this is 3 pi by 2 radians, or 270 degree, and this is 360 degree. Okay, so basically, if you see, it traces a sinusoidal signal. Okay, so that's the reason we say the waveform induction using a circular machine is a sinusoidal signal. Okay, so now what you have to do is you have to just join these points. Okay, let's do that. Okay, so that's your positive half cycle. And this is your negative half cycle. Okay. Now, what if the inclination is some theta, inclination is some theta. Let's say position 5. So in position 5, the vector is rotated by an angle theta, some acute angle theta. So the y projection is somewhere over here. What should be the x projection? I mean, the coordinate, sorry, coordinate. What should be the x coordinate? X coordinate should represent theta, right? So some theta here you have to mention. Okay. So this is your instantaneous value. Let's say this instantaneous value is, sorry, V1. This is your maximum value. This is your plus Vm. This is your negative maximum, which is minus Vm. So any arbitrary projection, if you consider, okay, basically it traces some instantaneous value. And if you were to consider, a huge set of instantaneous value, the more accurate sinusoidal wave tracing you are going to get it. Okay, so basically between 0 to 2 pi interval, you can have an infinite set of instantaneous values. Okay, but for the sake of explanation, we have considered a definite set consisting of 5 points. So every time, it is not so convenient to draw the AC waveform because waveform sketching consumes time. So instead of, representing a sinusoidal function with a waveform, you can also represent a sinusoidal function using a rotating vector. So that's the reason, in day-to-day life, people choose rotating vector over the graphical representation, simply because graphical representation is tedious or time consuming. Okay, so if at all you have been given with a sinusoidal signal, okay, let's say some V and time is t, you can represent this sinusoidal signal with a rotating vector. Where the vector length represents the maximum value of the signal, rotates in anti-clockwise direction. So a complete waveform can be replaced with a directed line segment rotating in anti-clockwise direction. So this is called as vector representation of AC quantity. Okay, so in our future discussion, sometimes we may consider waveform representation, or sometimes we may consider the vector representation. Anything is fine. Okay, but well, let us see the context and let us decide whether to use waveform or whether to use the vector. Okay, now I'll just stop at this point. Just want to ask, is it understood?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes,
fine.
sir.
Excuse me, sir.
Yeah, tell me.
So suppose if the EMF is induced across the conductor, won't the current flow through it and neutralize the EMF?
Across the conductor, in the sense, across the conductor, see, the conductor itself is considered as a unibody. Okay, whether you consider inside a part of the conductor or outside part of the conductor, it just represents a single coil. Now, in that single coil, okay, we will check the EMF based on the orientation of the conductor. If the conductor is inclined at some angle, there will be an induction of EMF. Okay, if the conductor is, kind of occupies a position which is parallel to the flux lines, then it is zero. So there is no fuzzy state in it. And moreover, it's something like what we are doing now. See, physically EMF is obtained and that EMF can be displayed on a cathode ray oscilloscope. But what we are doing is we are just freezing the motion and we are trying to build a mathematical analysis around it. Okay. So when you rotate the generator, you get a sine signal. On what basis it generates sine signal, that is what we are analyzing in this particular topic.
So I have a doubt, sir.
Okay.
So when the turbine spins, sir, the frequency of the wave produced is equal to the frequency of rotation, no, sir?
Absolutely.
So if the rotation of the turbine increases or decreases, won't the wave also change, sir? How is that accounted?
Okay. Now, yeah, it is there. Slightly, I will have to get into the depth. Okay. Now, with the increase in frequency, okay, the EMF can also be increased. That's because in case of AC generator, okay, eventually you'll see in module 4, your induced DMF, okay, is proportional to frequency as well. Okay, is proportional to frequency as well. But we will not change the frequency because at the destination, our systems have been developed to receive a frequency of 50 hertz. So in India, the electricity is produced at 50 hertz cycle. But if you change the, what you call the turbine speed, the frequency is going to change. Greater the turbine speed, greater will be the EMF. But as I said, we will not do it in reality. That's because our entire system is being designed to operate at 50 hertz cycle. But it is possible.
Sir, but then due to some circumstance, like there's more water or there's less water, will that change?
No. More water, see, in case of hydel power plant, if there is water, the generator is under action. If there is no water, hydel power plant is shut down.
Okay, so
And the power will be, the power will be supplied from different source, probably thermal power plant, wherein they have surplus this one. Because the backbone of hydroelectric power plant is the water head. If there is no water head, you cannot produce electricity. They'll simply keep that power plant under cold state and they start purchasing the power from elsewhere.
Okay, sir.
Okay. All right. So this is how, the concept of sinusoidal, or rather you can say the rotating vector concept is understood. Okay, so I'll go a little slow because if you are perfect with the concepts, probably we can pick up the speed later. Okay. All right. So what I will do, I will stop over here. Okay. So based on this, I will circulate a small quiz. Okay, and everyone are supposed to participate in the quiz. Okay. All right then. So shall we continue in the next class?
Sir.
Yeah.
Sir, is there any proof to say that the waveform, the sinusoidal wave representation and rotating vector concept both are same?
Yes. Yes. There is a physical model. There is a physical model. See, all this. This is not something like you propose. It's a proven fact. You do, and then you build your mathematical theory. Okay. Then only it is accepted in scientific community. Okay.
Sir, in the formula BVL sine theta, L represents the length of the conductor, right, sir?
Yeah,
What is the
it represents length of the conductor. Yeah, I did mention about it.
length of conductor in this case, sir, in the diagram?
Yeah, length of the conductor as in, see, now this what I have shown is as 1D. Okay, if at all I have to show you the 3D, something of this kind. Okay, this is the front view. What I have shown is the front view. Okay, this is the length, and the same conductor, okay, the trailing end of the conductor. Okay, it's something like this, man. In a wavy manner, they will lay the conductor. And if you look at the cross-sectional view, okay, the circular part you are going to see. Okay, so this is called as the length of the conductor. And it is not that one single conductor is there. There are a group of conductors, okay. I think, okay, so what I will do, I'll just circulate an image in the class group just to show you how exactly the conductors in a generator looks like. Okay, so this is the length of the conductor, and this is the flux density. Okay, B is the flux density of the system, flux per unit area of cross section, and V is the velocity at which the conductor moves.
Thank you, sir.
Yeah. All right then. Bye-bye. So we'll meet in the next class.
Thank you, sir.
Thank you, sir.